All right, here we go. Chapter 4, Chemistry in Context. In Chapter 4, we're going to talk about climate change. That is going to be the big topic that we will talk about. Now, this will be Chapter 4, Chapter 5, and Chapter 6 exam. So you'll want to get ahead on this, and you will want to attend the review on Wednesday, okay? Because it'll be on Wednesday that I'll start to tell you, this will certainly be on there. This will be on there. That's what happened on Wednesday. You won't hear it again any other time. Follow? So when we go to Chapter 5, if you ask what's on Chapter 4, I won't be talking about it. So everyone follow? So it's important for scores that you be here on Wednesday. Okay, so we're going to talk, what are the sources of carbon on Earth? Very important topic. How does carbon move between reservoirs, and how do scientists measure it? What's greenhouse gases? We will talk a lot about greenhouse gases and what's a positive and negative effect of them. They have both positive and negative, as do most of the natural materials. What are the global consequences of climate change? Very, very critical and very, very important. How do our climate trends differ from the past? We start talking a little bit about this in Chapter 3. How can my daily actions affect the global environment? And these are the things that you really are going to learn to talk about. You'll do a paper on this after the break. Okay? So let's get going with the carbon cycle. We'll take a look, and we're going to read through the verbiage first, and then we're going to talk through the diagram on the left of the slides. All right, there are three main reservoirs of carbon. In other words, there are three main areas where carbon can be found or stored in the Earth, and that is below in the troposphere. You could just subdivide these further, but this is just for grouping's sake. This is how they're historically and most often grouped. All right. The atmosphere in the form of carbon dioxide, about 400 part per million, and part per million, you can convert that back to percentages now, can't you? So you kind of see what the percentage is. You move a few decimals over, and voila, you have it, right? 0.04%. Okay. Then we have methane at 1.8 part per million, and carbon monoxide, trace amounts as a pollutant. So carbon monoxide in any form and anywhere is considered a pollutant, and that's important to know. It is also referred to as a silent killer. It sneaks up on you, it kills you without warning. You don't smell it, you can't hold your breath against it, and things of that nature. So you don't try to do that. Carbonate containing rock, fossil fuels, and soils. This is another really huge area of it, particularly fossil fuels, which are used for energy, for manufacturing, for all types of manufacturing. Then we have plants and animals, which many believe contribute to the fossil fuels as well, where carbon atoms are contained with oxygen, hydrogen, and nitrogen from carbohydrates, protein, and lipids. In other words, we have the animal source, we have the animal source here, and then we have the inorganic source here, and then we have the atmospheric. So if you had to group these another way, this would be that which is in the air, atmosphere. This would be that which comes from what we would call inorganic sources, and 3 would come from what we call organic sources. All right, the global carbon cycle shows the quantities of carbon in gigatons. Know that. That's one of my favorite true-false questions. Okay, it's what units is measured in. The answer is going to be gigatons. So it would be true if it's gigatons. Anything else would be false. That are stored in various carbon reservoirs, black, or moving through the system per year, red. Okay, so what you have here, if you look at the diagram, you have the carbon stored versus how it's cycled. And we know by the laws of conservation of matter that you can't destroy matter, neither can you create matter. You can transform it, you can transport it, you can use it, but you can't destroy it nor create it, and that's when it's called a balance. And when you see that in all the systems, like in yours, in the Krebs citric cycle and things of that nature in your body, there's this balance. What goes in is what comes out, and it cycles around and around. And in the Earth, we have here the fossil fuels, and you'll want to note, because one of the things I also like to ask is, what's the largest source? I always like to know the largest source of this, so you'll want to be able to know what that is. So here you have sand and silt, and you have about, 10 to the 3 gigatons there. You guys can probably see it a whole lot better than I can. And then you have carbonaceous rock, 10 to the 7, and fossil fuels, 10 to the 7. So here you have a really huge amount that's right in between here, fossil fuels and carbonated minerals in rocks, and the sand and silt itself. So this is really huge. And then we look at what's in the ocean. This is a fair amount, just the depth of the ocean area. So this would be land, and sub rock below the ocean floor. Here you have at the ocean floor, you have about 10 to 4 gigatons. So this is 10, 17. So about a fourth of that. Yeah, about 4 times. Yeah. And here we have also, a little less than a fourth here in terms of the soil. All right. Then the surface water contains a fair amount of carbon, and that's going to be, all the forms of algae and other types of things that are floating around the ocean surface. So when we look at the cycle, let's start here with photosynthesis, which is the source of life. You have carbon. You have carbon atoms, hydrogen atoms, and oxygen atoms. You have basically carbon, and then you have water. And they basically react through using photosynthesis to create organic material, your carbon chains, and the source of life. And they get photons from the sun. So this photosynthesis here creates through photosynthesis, we get about 61 gigatons a year. So it's pretty small compared to this. Is the really key point. Does everyone see that? This is pretty small. And so we go here, and it goes into the soil, and then the forest lets so much back into the air, about 1.5 gigatons. Again, these are all small values. Reforestation about a half, and it goes in this cycle. You have respiration. It's breathing. And it contributes to the cycle. And we have that from the ocean, the volatiles from the ocean, ocean gases, what have you. And here we have burning of fossil fuels that puts it into the air. And this is not natural. So be aware of that. The part of this carbon cycle that is not natural is the burning of fossil fuels. And you will want to know that. This puts carbon into the air that essentially doesn't allow it to maintain its natural balance. And when it doesn't maintain its natural balance, it creates pollutants. And that's what you want to watch for, is pollutants. There are regulations, and you know of one, right? Some of the regulations, like the Montreal Protocol, things of that nature, that help regulate these types of events. All plants have required regulation about the carbon footprint that they put out, and they have to stay below that, otherwise they get a hefty fine, or in some cases they have to shut down. It's rare that shutdown happens. Usually they find a way to rebalance it, and they promise the federal government that since I went over this month, we promise to go lower in the next few months to come. But this is what we look at. All right. Now, for those of you who start to frown about manufacturing, that's your cell. This is where you get your cell phone. This is where you get your nylons. This is where you get your carpets, your vehicles, your flat screen TVs, and whatever device your sportswear, your basketball, your football, your hockey gear, manufacturing. So it's not that manufacturing is trying to be a bad person. It's just the nature of the beast to produce what we as consumers like. So the regulations are put there to help balance this, hopefully to give Earth a lot longer future than it appeared that it was on a few years back. Okay? That's your carbon cycle. Be aware of this cycle. We'll come back and tell you some more specifics on Wednesday. Global carbon dioxide emissions. Here, this is what happens when it comes to carbon dioxide emissions. I always ask questions from this slide. As a matter of fact, you can almost bet there's probably a question for every slide in chapter 4. I'll bet you. Okay? And we'll talk more specifically on Wednesday what that looks like and how to prepare for it. Wastewater. It's only about waste and wastewater. It's about 3%. Take a look here. Power and heating stations. This is huge, right? Anybody lost their power? Anybody live around where lost power? Yeah, I did too. I lost my power, and I have a sump pump. Sump pump goes out, and so I had to choose this morning whether I was going to take care of the sump pump or my dog, because my alarm system's beeping, warning me of all the things that is connected to that the power likes. Yeah, I let the sump pump overrun. I took care of my dog. No, I didn't do that. Okay, but here's what's happening. We're saving a little bit today, is the point, because we're without power. Not by choice, okay? But this is huge. 26%, okay, of the carbon dioxide emissions. And you're going to find out why that's so critical. Comes from power heating. Does everyone follow what? I don't know how to say that. If you look at power heating, industry, and transportation, and then residential buildings, this is all because of lifestyle. Absolutely all lifestyle. So a large part of the carbon dioxide emissions in the air that are, by the way, contributing to greenhouse gases are lifestyle, effects of lifestyle. Again, I am not saying anything against that, but that is the fact, because it comes from manufacturing, okay? From some way of producing something so that we can have a better life, so the quality of our life, of how we live. And that's okay. That's why we have to manage it. That's why we have to be environmentally responsible, okay? So 26% power stations. Industry is 19%, and this is why if you get in an argument with someone from industry, well, industry is less than power station. Yeah, but the reason we have so much power use is because of manufacturing. Does everyone follow? Manufacturing is a huge consumer of energy to get us our cell phones again, and our skates and our Nikes, okay? Let's go over here to transportation. This is me. This is my truck, okay, that I am going to continue to drive because I enjoy it. Okay, so this is transportation here. This is residential buildings, some of which are turned off if you lost your power right now. So these are all large parts. I expect you to know. Yeah, I expect you to know these. This is an unfortunate side effect of lifestyle as well. Deforestation. Deforestation, one of the biggest areas of deforestation was the Amazon. And one of the biggest products that came from the Amazon was teak wood. Okay? Would you like to know what teak wood was used most for in the United States and Canada and Europe? I'm pretty sure of those. For judges, big judges' desks. That's when they sit behind the gavel. They wanted a really huge teak desk. That's what they sat behind. And to get that, took a lot of trees out of Amazon. But then once the judges had teak desks, well, those of the aristocratic class and those who were more wealthy said, you know what? I want a teak bed. So, yeah, a lot of teak wood. And saying it's like humor, but that's really what happened. So deforestation was really support that way of life. Same things happen in the United States, by the way. A lot of trees taken out for the same reason, for lifestyle, for trees and things that we enjoy. But deforestation on the Amazon was really, no one knew that it was happening. So essentially, when you hear the term that the Amazon's the lungs of the earth, it really was. It was that place where it could really balance the carbon cycle. And now it's struggling to do that because of deforestation. Now, I use only the Amazon as the example because that's where the major effect of deforestation was felt. And then we have agricultural. This is where we're growing our crops. And so this is a big adds to it. And you're going to see later that agriculture also adds to one of the largest footprints of nitrogen, the effect of nitrogen because of fertilizers and things of that nature. Now, I've told you about this, and I don't want to sound like this is doom and gloom. It is not. This is science. This is the science that we're living now, and with science, we learn how to be responsible once we understand the impact of the science. In many instances, the impact of these events were not known until after the fact. Follow? All right. It was really good for the economy, good for the world, good for the whole world to do these things. But now we're learning the effects of them, and this is where new programs are being put in place. Scientists are creating new ways to go about doing the same things they were doing to help improve the quality of the earth. Okay, that's carbon dioxide emissions. On Wednesday, we will also practice doing the math that's in chapter 4. And this slide will come back to see you on Wednesday. We will practice the math because you will see problems like this on the exam. This will be practiced on Wednesday. Okay. Today we'll take you through the lecture and we will practice it on Wednesday. How to do it in more detail. The atomic mass of each element in the periodic table is the weight average of the naturally occurring isotopes for carbon. Occasionally, if you see me looking around like this, most of the classes where we teach chemistry have periodic tables, except for this. This is one of the ones that don't. So if I'm looking around, I'm looking for a periodic table. On the periodic table, you'll find this value for the atomic mass or approximate, depending on which periodic table you get. We'll have this number. This number is an average weighted number, meaning that there are these things called isotopes, and that's what we're going to talk about here now. And you're going to practice doing the math for isotopes on Wednesday. So you have this average. So it's a combination of 3 forms of carbon that we show you here: carbon 12, carbon 13, and carbon 14. Okay, and this is what we call radioisotopes. Carbon 12, which is the most abundant, is about 98.9. Carbon 13 is about 1%, and carbon 14 is. These differ by the number of neutrons that they have. So carbon 13 has more neutrons than carbon 12. Carbon 14 has more neutrons than carbon 13. That's the kind of question I could ask you. So be aware of that. They differ by the number of neutrons. Okay, and because of the number of neutrons, it contributes to the mass. So carbon 13 mass of neutrons contributes here. Okay? So, for example, here carbon 12 has a mass number of 12. I think you recall I said to you, you don't use the numbers on the periodic table. I have to tell you what the mass number is. So, for example, a mass number of 12. You've done this in chapter 1 and 2, I think it was. You have a mass number of 12 on your periodic table, which you don't have in front of you. You can flip to it if you wanted to. But the number of periodic C12 has 6 protons, is atomic number 6. Just gave away my answer. Has atomic number 6, therefore it has 6 protons. Okay? And therefore, because it's neutral, it has 6 electrons. And 12 minus 6 gives us 6 neutrons. Does everyone follow what I just said? We just went through this. You're going to do this again on Wednesday. Carbon 13, on the other hand, has a mass number of 13. But it is carbon. Therefore, it is the same atomic number of 6. Therefore, it has the same number of protons of 6. It has the same number of electrons of 6 because it's neutral, but its mass number 13. Therefore, it has 7 neutrons. So everyone follow what I just went through and said. And we're going to practice this again on Wednesday. So therefore, carbon 17 has 7 neutrons. You will have a question like this. For those of you having trouble grasping this now, I suggest you at least write somewhere on your slide that the number of neutrons in carbon 12, that's going to be 6. Going to be 6, whatever number I just told you. 6, whatever number, 7, and did I get to 8? What's 14? Yeah, did I say 7 in the last one? 8, I apologize. 6, 7, and 8. Okay? All right? That's Monday morning math I was doing. I apologize. So we will practice this, okay, because you will have to do this okay? Atomic masses are expressed in unified atomic mass units, and this is what it amounts to. It's really 10 to the minus 27 kgs. So it's atomic mass units, and so the mass number is the number of neutrons plus the protons, and that's what we just went over with you. isotopes have equal number of protons but different number of neutrons. And so here we show you, it's right here on the slide, 6, 7, and 8. So make sure you memorize that. That's 6, 7, and 8 here. You're never asked to memorize this. You're never asked to memorize this. But if it says C12, it tells you that's the mass number. If it says C13, I'd ask you the mass number. That would be 13. If it says C14, it's 14. There's no trick to this. I can't say what's the mass. What you get it? If I say C14, I am giving you the answer of the mass number. Does everyone follow? If I give you the mass number, I just told you it's C13 or C12. Does everyone follow? There's no magic to this. I don't teach tricks with that to try to throw you off, okay? But you don't have to memorize this. I don't require that, okay? Just be aware of this and know how to do the calcs, which we'll do. And so this is how it typically looks on the periodic table, but periodic tables have been so redesigned until this number might be at the bottom, they might both be at the top. Be aware that the small whole number is your atomic number. The mass number will have decimals, okay? And these are by the SI definition. And what this amounts to is that the mass number, well, this is actually, okay. This is actually the weighted average. This mass numbers should be like this. Your weighted average mass is also, it is per 1 mole unit. Know that. Your average, okay? Your weighted average, which is this number on the periodic table, is for 1 mole. So we have 1 mole of carbon, it has a mass of 12.01. The atomic mass number would be a whole number. It would not contain decimals. Okay? So a mole of atoms of any element has a mass in grams equal to the atomic mass of the element in SI units, as atomic mass. Okay? Unified atomic mass units. Okay? So all the mass that you see in the periodic table is for 1 mole. Okay? So if you had 2 moles of that, how much would it be? Approximately. Just times 2, right? So that kind of math, you just don't try to overthink it. If it were 5 moles, you look on the periodic table, and it's 5 times that number. Does everyone follow? Don't overthink it. Okay? All right? This is for 1 mole. So, all right? We will practice that on Wednesday. We will also practice this. 1 mole of carbon, so this is what we're just talking. 1 mole of carbon has a mass of 12.01 grams. So 1 mole of carbon equals 12.01. And these units are always expressed in gram/mole. So gram per mole. If you have 36 grams of carbon, we just did that. You just do the calcs. We're going to walk through how to do what we call dimensional analysis on Wednesday. 2 things are going to happen on Wednesday. We're going to review chapter 4. We're going to practice the math in chapter 4. And this will be the only time we're going to do that. We will not return to that when we go to chapter 5 and chapter 6. Okay? So we will practice these types of things on Wednesday. When we think of counting atoms, it was very, very challenging feat for the early scientists to figure out how to do this until one brilliant guy, Avogadro, discovered and found, oddly enough, that there was 1 mole of anything equals that number of Avogadro's numbers. So 1 mole of anything is that number of Avogadro's number. 1 mole of students is 6.02 times 10 to the 23. 1 mole of vehicles. Does everyone follow? 1 mole of anything is this. This is how we count atoms. It's a unified method of counting atoms that stood the test of time. Okay? So, all right. So 1 mole of carbon is equal to that number of atoms. So if you want to know how many atoms of carbon you have, right? So it's 6.02 times 10 to 23. So what if I had 2 moles of carbon? I would do what? 2 times that number. Now, for those of you who struggle with the math, you don't say 2 times the the power, the times 10 to the 23. Okay, it's just 2 times the first part of the number. However, that's going to give you 12, and then you have to put it in scientific notation, which is going to give you 1.2 times 10 to the 23. Got it? Okay, we'll show you how to do that on Wednesday. All right, does everyone follow? We will show you how to do that, yeah.
Will we have to memorize Avogadro's number?
No, I typically give you that. I tend to give you Avogadro's number in the calcs. In the upper classes, we give it to you, but we ask you to memorize it because if you're in chemistry, if you're walking down the hall, you see a person in the mall, you're out on the dance floor partying, you're at spring break and you're a chem major, someone just walks up to you. That's one of the conversations always comes up as a chem major. Hey man, what's Avogadro's number? So we ask you to memorize it then, but since you're not chem majors, we won't hold it against you. I give it to you, okay? I typically don't ask you to memorize conversion factors and factors like that, okay? But I expect you to be familiar with it, okay? How to use it is what I tend to do. So that's what this means. So if you have 2 moles, and thanks for asking the question. If you have a question, make sure you stop me. All right, so if you have 2 moles of carbon, it's times 2, right? 3 is times 3, 4 is times 4. Does everyone follow the general process? Okay? And so this type of math, you can use finger and toes math. You don't need a really deep calculator to do the type of math we're going to have you do. And since you know most of my questions, the answers are going to be on the exam. All right? You're usually choosing one. In 102A and 102B, the answers are always on the exam. Okay? You just have to work them out. Okay?
Can we use calculator?
You can if it depends on the exam. I'll tell you whether you can or cannot use a calculator. Okay? For example, this would be one that I expect you to be able to do with finger and toes math. Does everyone follow? This is just 2 times the number. If you're going to use a calculator, you'll know by the next exam. Yep. I'll tell you on that date. So be ready to do it with your fingers and toes. Molar mass. We're going to do this. Also, we're going to work through these problems. So Wednesday will be a work day. What happens on a work day like that? I bring in all the questions on the exam. On the paper, it's almost like a quiz. It's almost like I give them to you. You start to work them with your partners, with me. We all work until we work it out, and we learn that way. Okay? So you can bring all the notes. You can work with your partner. You can call your grandma. If your dog can do the math for you, you can bring your dog to class on Wednesday. Okay? Got it? Atomic mass. So this is what we have for atomic mass. And what we learn to do is convert between grams of moles and moles of molecules. Why is this the case? Each of these allows us to be able to manipulate the science. It's why we go from grams to moles to molecules. For example, we cannot, on an analytical balance, weigh molecules. We can't do it directly. But we can directly weigh grams. So if I'm in the laboratory, carrying out an experiment in the laboratory, I would be looking to use grams. Follow? Now, when I carry out reactions, I react compound A with compound B, okay? Or maybe I just do photosynthesis and have carbon plus water and sunlight photons. I have to have a ratio of moles that allows that to balance the equation, a ratio of materials that allows that to balance the equation. That balancing occurs through moles. Therefore, I have to be able to calculate the moles. However, if I'm going to deal with molecules, I need to know how much space and can be filled and how much, particularly if I'm going to do NASA-type work, I need to understand something about these molecules and what space they're going to cover, what space, they're going to be in, okay, and what space they're going to cover. I have to think about molecules because there's only a certain number of molecules perhaps we'll be able to interact in a certain fashion that's useful for the particular application. You get it? All right, so this is why. So depending on where you are in doing your work or your research, you do it. A lot of physicists work over here. A lot of engineers work here. Chemists work across it for the most part. So now, why do we talk about all of that? This is how we learn about the carbon cycle and where the carbon is and the quantities of carbons that's affecting our environment. Okay? And on Wednesday, we're going to practice doing those calculations. So, we've talked about the carbon balance, right? But we also now have to talk about that energy balance. How much energy is balanced here? You now know about UVA, UVB, and UVC, right? You know that UVC is 100% blocked by ozone and oxygen in the stratosphere. You also know that part of UVB penetrates, but most of the UVA penetrates. And so we're going to talk about what happened when these rays penetrate on this slide, Earth's energy balance. Okay? 46% of the sun's radiation is absorbed by the Earth. That's a fair amount. The other 54% is either absorbed in the atmosphere or reflected from Earth's surface or atmosphere. Okay? You got it? So about half of the sun's absorbed, and that's what you want to kind of hang on to that. Now watch this, and we'll talk about the diagram on the left in just a minute. Of the 46% that is absorbed, 37% is reflected in the form of infrared. Infrared, right? You know what infrared is, right? That's on the electromagnetic spectrum. It's adjacent to what? Visible. So you have visible and you have infrared. And infrared is not harmful to us. Infrared is what heats the Earth. And so if infrared is not causing any problems, certainly going over to shorter wavelength microwaves and shorter wavelength radio waves won't cause a problem. Does everyone follow? Infrared for us is a healthy part of our environment. We need infrared to maintain the heat balance of Earth so that we can grow our plants and cucumbers and cauliflower and broccoli. Okay? And an occasional banana or peach. Follow? Okay? All right. Again, infrared radiation that is absorbed by the atmosphere. This results in greenhouse effects with an average temperature around the Earth of 15 degrees C. So the average temperature around the Earth is 15 degrees C, all right, or 59 degrees F. Greenhouse effect is how the Earth balances the heat. That is the natural source of balancing the heat. That statement isn't in your notes here, but I would write that statement down because that's how I like to express it. The greenhouse gas effect is the natural means by which the Earth balances its heat. Okay? And so now it has a balance, right? So what happens if I throw something else into that? It throws it off balance. Does everyone follow? If I take something away, it throws it off balance. That's what creates a negative greenhouse effect, or a greenhouse effect too hot for us to handle, or hotter than the average temperature. Does everyone follow? So it's not that greenhouse effects is bad. That is naturally how the Earth balances its heat. But when the balance is disturbed by man-made materials that we put into that, then that balance causes bad effects. Does everyone follow? So greenhouse effects by itself is not a bad thing. Now, typically when you hear it in the media, it is talking about the negative side of greenhouse effects. Does everyone follow? So the natural side of it has been taken as the common denominator. We know that. So when you hear it talked about, you don't hear the common denominator is that's normal. The greenhouse is a normal part of the process. But in science, we like to talk about the natural part of it first before we talk about the deleterious effects. Zero follows. Okay? So this is how it balances, and this is healthy. So the energy balance on Earth's energy balance slide is a healthy. So let's look at the diagram. We have the sun, 100%, hits the atmosphere, okay? And once it hits the atmosphere, we know we have the two vital parts that we talk about in this class, the stratosphere and the troposphere. Once it hits the atmosphere, we get 46% hits the Earth and is absorbed here in some form, including by us. right? So you get some type of absorption. Then you have, that 26%, once it hits the atmosphere, 23% of that now gets trapped here. You have a huge portion that gets reflected back out into the atmosphere. Then you have some off the surface. Not much of the surface reflects off. Maybe we should all go out with mirrors and send it back. No. Okay, but it gets reflected off the Earth. Then the Earth emits so much, absorbing the atmosphere, emitting the atmosphere. This entire balance is what keeps this 15 degrees C temperature. This is the process for it. No, do not memorize all these numbers. If you're aware of this, the numbers in this first part here, okay, we're okay. I don't expect you to memorize all these numbers, but I do expect you to know that less than 100% of the sunlight, right, stays in the Earth. It goes back, and these are the numbers for it. Without the natural balance, the average temperature on Earth would be minus 18 or 0 F, and the oceans would be frozen year-round. Okay. This is why the natural balance is so important. In the case of this, we're getting greenhouse warming. So if we reduce the amount of infrared, the oceans would freeze, right, without this balance. What happens if we increase the amount of infrared? Things melt. It's just natural science. You get it? And this is what we believe is contributing to what's called the melting of the polar caps. Because the amount of infrared is increased, and you're going to learn why that is the case. Okay? So more heat, we start to melt things. So this helps us now to start to talk about the shape of these greenhouse gases. And from this we'll understand why some of the materials that we've manufactured affects that. Greenhouse gases absorb radiation at a defined frequency. Recall the example I used of your cell phone frequency or the frequencies in infrared spectroscopy. You guys aren't taking the lab, so you're not doing that. But the Sirius radio frequency, that exact frequency. I'm just using examples of exact frequencies. So it absorbs, and the reason it absorbs is because of its shape. There are some unique shapes where it absorbs and the infrared, and they really like that. And it absorbs even more and increases the amount of infrared there. So let's take a look at the verbiage here. 80% of infrared radiation emitted by Earth is absorbed by the atmospheric gases. So 80% of the radiation is absorbed in the atmospheric gases. You get it? So if we affect those, then we change this 80%. Does everyone follow? Okay. All right. The absorption of infrared causes molecular vibrations such as bending and stretching. This is important, and I think we had that on the last exam. Infrared causes bending and stretching. And that bending and stretching is what allows the molecules to bounce back and forth. That keeps it warm, keep the warmth. Okay? Bending and stretching. So the molecule bends and it stretches. The gases, the infrared hits it, its shape, and it bounces back and keeps the Earth at its temperature. Why do carbon dioxide and water vapor, infrared, not nitrogen or oxygen do that? Here's the bottom line, and we're going to talk more about this. Nitrogen does not have a geometric shape that allows it to absorb the infrared radiation that we're discussing. Okay? It does not have a geometric shape. Okay? Nitrogen rolls around like a ball rolling down the slide or something. Okay? Water, has anyone ever seen in their life a slinky? Okay. This is more like a slinky going down. It's a little toy that pops over and over and over. It's like a walk down. Okay? Okay. So this is a little bit more dramatic for water. It sticks as it goes down. This just rolls down. It's a marble. So the infrared doesn't match the frequency. The bottom line is the shape of nitrogen does not allow for a frequency match that causes for the bending and stretching of the molecule to affect greenhouse atmospheric temperatures. That's why it doesn't function as a greenhouse gas. It doesn't have the shape. What carbon dioxide does. Molecular vibrations are related to the shape of the molecule. That is the critical point. In order to predict molecular shape, we'll have to visit Lewis structures. Recall Lewis structures in Chapter 3. We ask you to memorize certain ones. And then identify the arrangement of electrons so that they are far apart as possible to limit their mutual repulsion. In other words, you have to draw a really good Lewis structure. And when molecules are formed, they form where they really they like their space. Each of the atoms likes their space, so they will push themselves around until they find the maximum space. So if you have a central atom, for example, carbon dioxide is carbon with 2 oxygens. This molecule will push itself until those oxygens far apart from each other as they can. In the case of water, you have water and hydrogen. They will push themselves away, but you have this lone pair that pushes them back down, and it forms a bent shape. Okay? So they can reduce the amount of repulsion between each other. And then, okay? So here they are. One of the major shapes that contributes to greenhouse gases is what's called tetrahedral. That's what you see here. I'll read the verbiage in a minute, but let's just explain the diagram. This is a proper Lewis structure. Okay? This is a Lewis structure drawn in a stick form, where each of the 2 electrons equals 1 bond. Here is more of a geometric projection of it, where the atoms are going back, this is coming out, and these 2 are in plane. So it's like a stand on a music. It's like on the bottom of a music stand. This shape is particularly sensitive to greenhouse effects. That's the bottom line. The tetrahedral shape is particularly sensitive to the greenhouse effects. You might want to write that down. Okay? Tetrahedral shape. Okay? The tetrahedral shape is particularly sensitive, okay, to greenhouse effects because of its geometric shape. I said that's almost like I said the same thing twice. Tetrahedral means it's geometric shape. Okay, but the particular geometric shape of tetrahedral is very sensitive to greenhouse gases. This is a natural gas, methane, that comes out of ground. Okay, and this is why some who don't believe in global warming say, well, methane's put into the air. Okay, yes, it absolutely is. And it comes out of the earth, it absolutely does. And it contributes to the greenhouse gases, it absolutely does. But here's the catch, folk. That's nature. That's natural. Nature had already accounted for its balance. You can't destroy matter, or you can't create nor destroy matter. The earth has a certain balance of matter, and that balance of matter has been here for whatever billions of years the earth has been here. And that balance is part of its cycle. Does everyone follow? Okay? In manufacturing, we took a portion of those materials and we transformed it into species that the earth was not accustomed to balancing. So to argue that the natural methane is just as bad as something that we created is not true, because that natural balance was already there. Does everyone follow that? That's important to note. You can't create nor destroy matter. Okay? But you can transform it into things that are more harmful to the earth. And that's what happens many times when we do certain types of manufacturing. Let's go through and read the verbiage here, okay? Let's see. We've done this already. Yeah, I'm just going to read through really quickly here. We've done this already in terms of doing Lewis structures. The Lewis structure for 102A, which would be slightly different from that for 102B. I will give you the sets that I want you to memorize and know. In 102B, you will actually have to draw them from scratch, okay? They won't be ones that you necessarily know. So we draw Lewis structures. We arrange the octet rule, right? And we've gone through these in Chapter 3. And so in your case, I will always give you the central atom. You'll be looking at it, okay? And here's how you'll know a tetrahedral shape. You ready? Simplify it. Get ready to write this down. You should never miss this on my exams in terms of what a tetrahedral shape is, because for 102A is going to be limited. 102B will be more than that, okay? In 102A, your tetrahedral shapes will have for its central atom something from the same group that carbon is in, and carbon is in group 14. Does everyone follow? So your central atom for tetrahedral will be group 14. If it's from group 14, okay? So everyone follow, that's for the central atom. And then it will have 4 groups around it. So everyone follow. Okay? So central atom, so you look at a central atom from group 14, and if it has 4 groups around it, that is called tetrahedral. It is that straightforward. It is tetrahedral in that fashion because the Lewis structures that you draw reduce their amount of repulsion by assuming that shape. Okay? Does everyone follow? So for every Lewis structure you draw from there, does everyone follow? With me? Got it? Okay, that's good to know. All right, so hang on to that. We'll tell you some others, and I think they might come up on the next slide. I hope they do. Yeah, we'll get to the others. Okay? So this takes care of tetrahedral. The tetrahedral shapes will come from group what? 14. Carbon. And 4 species around it. It has to be group 14 and 4 species around it. That's tetrahedral. If it's tetrahedral, it is a greenhouse gas. Some other examples of these greenhouse gases are what you saw in chapter 3, what we call CFCs, your chlorofluorocarbons. So you'll want to note that. Chlorofluorocarbons are greenhouse gases. So are the alternatives in chapter 3. Go back, look at chapter 3 slides. So are the alternatives to chlorofluorocarbons. They are also greenhouse gases. I expect you to be familiar with any of those. Okay, if they're drawn if they're on the exams. All right? Okay.
Wait, can you repeat that?
Yeah. Your greenhouse gases in chapter 3 include chlorofluorocarbons. So look at chapter 3, look for your chlorofluorocarbons. These were freon is the example. And also the alternatives to freon. And you'll see those. And the slides are listed as such. They're marked as chlorofluorocarbons, and it's labeled as alternatives to chlorofluorocarbons. But they're also they're all greenhouse gases. Okay? But the chlorofluorocarbons also produce radicals that destroy the Chapman cycle. The alternatives don't destroy the Chapman cycle, but they increase the heating in the earth. Okay? We're talking now specifically about molecules that increase the temperature in the earth. Okay? All right? So we have tetrahedral shape. Here's the other shape that we have. Okay? This is called pyramidal. It's pyramid. Let's correct this slide. I should have put it on here. This happens because we have what's called a lone pair of electrons on nitrogen. So any of the groups look where nitrogen is, right? Okay. So this would be 15. Group 15 should be. Group 15. So we have nitrogen. It has a lone pair of electrons, and what it does, it pushes these molecules down, and that shape also is a greenhouse gas. So pyramidal is also a greenhouse gas. Pyramid, P-Y-R, etc. A. M-I-D-A-L. Okay? So as in pyramid. It's also a greenhouse gas. So a lone pair occupies a space where the bond electrons, which influences the shape. So this lone pair pushes the hydrogens down into a shape that makes it like a pyramid. All right? And that causes it to absorb at an infrared frequency that increases heat. This is ammonia. So where do we get ammonia? From cleaning solutions. You get it? So the more ammonia cleaning solution we have, what happens? The more we can increase the greenhouse gas, because you can't get rid of, right? You can't destroy nor create matter. So once you have the ammonia, you have the ammonia. You can transform the ammonia into something that's less harmful, but if you just use the ammonia, it's going to happen. One of the other things that that's tetrahedral, by the way, were the hairsprays that grandma used. The big fluffy standout hair, right? You look at your grandma old pictures and you say, Grandma, right? When she had on a tie-dye t-shirt, okay, all halter top, and you can't believe that was grandma. Yeah, that was grandma. And the hair out here, okay? Hairsprays. So they were changed. A lot of it was changed. So this is an example of a pyramidal ammonia. Be aware of those. This chart summarizes then several of the shapes. Let's skip for now to bent for water, because bent water also is a greenhouse gas, but it's a helpful greenhouse gas. Keep that in mind. Okay. So basically, these shapes will reflect in some fashion or to some degree that we show you here. Carbon dioxide is linear. It's also a greenhouse gas. Okay. So you will want to be familiar with these shapes as greenhouse gases. And I'd like to, and maybe I'll know by Wednesday which ones are going to definitely be on there, but you can guess tetrahedral, bent, and pyramidal is going to be on there. Carbon dioxide will be there too. If one's missing, it's probably going to be trigonal, but since you learned these four, you might as well learn the fifth one. You get it? Okay? So be aware of this. We'll talk more about it. So here's what they look like. This shape, its best Lewis structure is shown here, and that minimizes the repulsion between the atoms, and it fits the octet rule, 2468, 2468, 2468, and this is a simplified form of that, and this is what the space field model looks like with the electrons of volume. This is the space they fill. If we take water, this is a reasonable Lewis structure, 2468, 2468. Hydrogen only likes to have two, and so therefore it's happy, and therefore we have two lone pair. These two lone pair push the water molecule down into a bent form. But actually, this bent form is somewhat like a tetrahedral, with the other two electrons occupying the other orbital regions for the tetrahedral. You get it? So bent is somewhat like tetrahedral. The two electrons occupy that space where the tetrahedral would be. So you have really four areas of space filled around it. Similar in the case of, let's go back to ammonia. You have 1, 3, 4 areas of space filled here. This occupies an area of space here, but notice it's 107 degrees, where that's 109, so not quite tetrahedral, you see, but it's pushing it in that direction. Notice here that this is 104, so those lone pair really kind of push those around and push them in a bit more, and that's what makes us have those shapes. All right, so let's read the verbiage here. For molecules with two atoms bonded to the central atom, the shape will be linear if there is no other lone pair. Memorize that or be familiar with it. I will not be asking you this as a definition. I will be asking you this. Does everyone follow? I will draw structures like they should look and ask you. By the way, I guess I should mention that ozone, which you are familiar with, it is also bent. We talked about that in chapter 3. So this kind of tells you how to do minimizing the repulsion. And so at the end of the day, what I expect you to be familiar with is that the reason atoms adopt their shape, so here's kind of a summary for those of you who like to write these summaries down. The reason the atoms adopt their shape is because of electronic repulsion, to minimize electronic repulsion. But actually, electronic repulsion also causes it, okay? But it likes to minimize, okay, the energy between the atoms and the electrons. So it adopts that shape. This brings us full circle back to electromagnetic radiation. Okay? Molecules behave different when they're exposed to certain regions of the electromagnetic spectrum. We've been talking about that. UV causes bonds to break. That's what creates radicals. Infrared radiation causes molecules vibration of stretch and bending. Microwave radiation causes rotation. You will want to know that, and I think we've already asked it in Chapter 3, which means that this could show up again in Chapter 4. Take a look. We have UV radiation comes in and it pops the molecule. This is why it's on the more energetic, higher frequency, shorter wavelength side of the electromagnetic spectrum. Then we have the visible, which is where we enjoy our life. We look at each other, we see things. And then we have infrared, which it vibrates and stretches. So the molecules vibrate and they stretch. And then microwave simply rotates, and it rotates it and allows you to pop your popcorn or make your oatmeal. So be aware of this. The energy and vibration and absorption properties of elements and compounds is related to its valence structure. Its valence electron structure is based upon the number of electrons. The number of electrons influences a property that is called electronegativity, meaning how electronegative is the species. I would tell you that the most electronegative is going to be in your upper right-hand corner of the periodic table, which means fluorine. Okay. And so it runs on that type of diagonal. It's where electronegative. In general, if it has more electrons, it tends to be more electronegative. If it has more electrons and if it has more valence electrons and it has those valence electrons at a lower row number of rings, example row 1, okay, then it's going to be more electronegative. All right, so the fewer rows, the fewer rings, electron rings, the more electronegative it is. Okay, that's why, for example, everything in group 17, which is your halogens, which tend to be diatomic halogens, which you now know. You learned that in Chapter 1. So you have the diatomic halogens. They all have 7 valence electrons, but the most electronegative is fluorine because it only has 1 ring around it, 1 row. It's in row 1. Okay? So, electronegativity refers to the measure of atoms' ability to attract bonded electrons. That's the formal definition. Okay? Think of it as tug of war of electrons. So essentially, atoms, when they come together, they argue and they debate over where the electrons should be. Some like to share those electrons equally, and others don't like to share. Some, in fact, decide they hate sharing so much that they get a divorce. Say, I'll take all the electrons and you get none. Okay? So the sharing of those electrons is influenced by where they are on the periodic table. Electronegativity, we just told you that, increased from bottom to top and left to right. In a bond, the more electronegative atom would carry a partial negative charge. You will want to memorize this. You will be held accountable for knowing what they look like. And on Wednesday, and I'm sure I'll remember to do it, we will show you more examples of what this looks like to do electronegative. So Wednesday you don't want to miss. We work through all of these things. We'll show you how to ID an electronegative species. Okay? As bonds are stretched and bent in a molecule, a charge distribution of the molecule will be affected. If the geometry and direction of the stretching bond cancels the charge, then then infrared radiation will not be absorbed. Okay? In other words, if the atom has different elements around it, it tends to absorb infrared when it is in the form of one of the shapes that we've taught you about. That's kind of a summary way of thinking of that. Okay. Here we show you again the molecular geometry of these. These are the types of motions that can occur. We can have stretching, okay? We can have twisting, bending, and that's really what happens. And when that happens, the charge distribution is different, and that charge differential tends to affect how it responds as a greenhouse gas, okay? When that happens, we can measure it. And this is a critical point to make and to understand. We know what gases are in the atmosphere because of a method we call infrared spectroscopy. Okay? And what happens in infrared spectroscopy, as infrared radiation absorbs, the amount of radiation that makes it through the sample is reduced. Okay? Stretch and absorption occur at a lower wavelength, higher energy than bend and resonance. Basically saying, here it bends, here it stretches. What does all this mean? Some really bright scientists found that if they shine, if you will, an infrared signal on a sample, on these molecules, they discover here it will go along with no response, no response, no response, no response. And when it stretches at this frequency, the instrument measures it. And when there's nothing else, it goes here, here, here. When it bends, it's detected here. And this is just math. So they figured out a way to do the math and an algorithm such that when infrared is there. And what they discovered is that each molecule has a unique infrared spectrum. That's worth noting. Each molecule has a unique infrared spectrum. Therefore, we know exactly which molecules we're measuring in the air. We know when we're measuring, for example, we know if we're measuring methane, it has a unique spectra. It goes along, and when its freaks and match happens, it bends and stretches a certain way. That's different when ammonia goes along and bends and stretches from when barium chloride bends and stretches, from when water bends and stretches, and carbon dioxide stretches. And carbon dioxide, water, ammonia, and methane are studied a lot. And when it comes to greenhouse gases. And they all have a unique infrared spectrum. It's essentially, the infrared spectrum is the equivalent of a fingerprint, okay? It's unique. You know that's methane. You'll hear people say, well, how do they know it's methane? Well, it has a unique fingerprint, okay? Or perhaps you might think it was DNA, but I prefer fingerprint, okay? It has a unique fingerprint match. And when that and so this is a fingerprint match, the infrared spectrum for CO2. This shows the areas where it absorbed and where it stretches, and this shows where it bent, and this shows where no real activity was occurring in at these wavelengths. You know what wavelengths are now, right? So you're going from what? A higher frequency, shorter wavelength, you get it? We're scanning the whole thing to a lower frequency, get it? Longer wavelength. So everyone follow when we scan this, okay? And this is the amount that it transmits. No transmits, nothing. Lots of transmission. You get it? Or at least lots of transmission, no transmission. Just letting it all through right here, lots of transmission, no transmission. So everyone follow that, okay? So it goes from here it's transmitting, none. A lot, none or low. Then a lot, some, zero. Get it? Transmission. And that is a fingerprint. This is what water looks like. A lot of activity in water. You see it? Completely different. And that's what we want to make sure that you know. Water just looks different. No, I'm not going to ask you to memorize these spectra. So here you see water. Lots of places where no transmission. Here, lots of transmission, no transmissions, okay? This spectrum shows that water is a very effective absorber of infrared radiation and is a greenhouse gas. Because it's very effective at absorbing the infrared, therefore it is a greenhouse gas. When a molecule effectively absorbs Okay? Infrared, it makes it a greenhouse gas. Okay? And let's see, to do reflective percent and this reflective, same thing. Similar principle here, except we're using a reflector transmittance. I think we'll finish this. No. Maybe a good place to stop. So we have a lot to do on Wednesday, folks. So we'll see you on Wednesday. We'll finish this.